Thank you to Novium, the team behind the hover pen, for supporting PBS. Around 2 billion years ago, life had plateaued in complexity, ruined the atmosphere, and was on the verge of self-annihilation. But then something strange and potentially extremely lucky happened that enabled endless new evolutionary paths. The first eukaryote cell was born. This may also explain why there are no aliens. Hey everyone, before we get started, 2 quick announcements. First, we did our first Patreon livestream interview with Dr. Matt Kaplan, and if you haven't seen it yet, there's an unlisted link in the community tab and in the description. Join us on Patreon if you'd like to participate and ask questions in our next scientist conversation. Next, our merch for May. It's time for you to choose a side. You can selfishly maintain your own thermal equilibrium at the cost of hastening the heat death of the universe with our Entropy Strikes Back t-shirt or sweatshirt. Or you could join the resistance, signaling your opposition to entropy with our smart thermos. But chaos is the natural order, and so these items, along with last year's The Force equals mass times acceleration tee, will only be available in May on the merch store. Maybe you believe that the aliens are here, that they're watching us, waiting till we're ready, or that they're in the government, or are the government, or saw us and just left in disgust. But in lieu of any credible evidence, it's more rational to default to the null hypothesis that the Milky Way galaxy is not swarming with technological species. But that fact is surprising in light of everything we know about the huge numbers of potential places life could have arisen and the many millions of years head start some of that life would have had on Earth. This crude statistical calculus is the heart of the Fermi paradox, articulated by Enrico Fermi with his "Where is everybody?" And that was in 1950, long before we knew about the 10 billion plus Earth analogues in the Milky Way alone. As surprising as the so-called Great Silence may seem, there's a reason for it. We just don't know what it is. There has to be something wrong with our simplistic calculation that aliens should be common. That something, or somethings, is often called a great filter. There's one or more steps in the transition from promising but non-living planet to galaxy-spanning civilization that is so improbable that very few potential civilizations complete the journey. That great filter may be ahead of us. Maybe plenty of planet-spawned 21st century style civilizations, but almost all go extinct or fall quiet before revealing themselves to the galaxy. That sounds scary. But we also have reason for optimism that the great filter is in our past. That we, humanity, are one of the few to survive a brutal evolutionary gauntlet, and that we look towards a future unmarred by a statistical dead end. A past great filter is some event in the development of life and civilization that is so improbable that it almost never happens. This could be the initial formation of simple single-cellular life from a chemical soup, abiogenesis, or it could be some step in the transition from simple to complex life and eventually to intelligent life. On Earth, life started surprisingly early, within the first 10% of the planet's life at the most. This suggests that there's a high probability that life will form given reasonable conditions, otherwise we'd expect it to have taken more of Earth's 4.5 billion year history to take that first step. In that case, simple life may be very common in the universe, and we're quick to find hope of this in, for example, the organic molecules that we find on space rocks, which we talked about recently, or in the very tentative detections of possible biosignatures in exoplanet atmospheres. Although life on Earth formed quickly, it took the subsequent 3.5 billion years to get humans. And now we have at most 1 billion years left before the warming of the sun renders Earth uninhabitable. If life formed late, we may have emerged just in time to watch the oceans evaporate. So maybe an early abiogenesis is necessary, even if abiogenesis itself is a low probability event. This is an idea from David Kipping and his Cool Worlds lab, and David has a fantastic video on his channel. But let's pretend for a moment that simple life really is easy to form given the right conditions, and therefore is common throughout the galaxy. If we want an early great filter, we have to look elsewhere for our unlikely event. There are a few obvious seeming candidates. Any of the mass extinction events that wiped out most life could instead have wiped out all life. But no, we keep getting hit by asteroids and extreme volcanism and maybe even supernovae and gamma ray bursts, and we just bounce back. Perhaps then the transition from unicellular to multicellular life was a colossal fluke, and so most planets are covered in slime molds and not much else. But actually, multicellular life evolved independently several times, so it can't be that unlikely. But there is one innocuous seeming step in the evolutionary path that definitely only happened once, and so is a candidate for a colossal fluke. It's the formation of the first eukaryote cell. It was this event that enabled a massive increase in complexity of life, including the transition to multicellularity. It made life diverse enough to survive the current and ensuing catastrophes and to fill all corners and ecological niches of the planet. Eukaryogenesis has been talked about as a great candidate for a great filter, but there's a recent study that makes it even clearer how game-changing this one event really was. So let's see how a freak accident of biology can explain why we don't see aliens. Just over 2 billion years ago, two cataclysms hit the Earth. The evolution of photosynthesis in cyanobacteria led to this green slime covering the planet. We still see the fossils of these algae beds. The byproduct of photosynthesis is oxygen, and after some hundreds of millions of years, the respirating slime filled Earth's atmosphere with oxygen for the first time. This great oxidation event killed nearly everything, which in turn may have precipitated the next cataclysms, a glaciation event exceeding any later ice age, leading to a snowball Earth epoch. Together, these events placed colossal stress on the life at the time, which was still exclusively prokaryotic, single-celled life, bacteria and archaea. And that may have been the end of life's brief tenure on Earth were it not for one incredible adaptation. Around this time, a lone archaeon, probably a stressed out one, happened to absorb a bacterium. Perhaps with the aim of digesting it, or maybe the bacterium was some sort of parasite, but the bacterium not only survived and thrived inside the protective environment of the archaeon, but it provided a surprising benefit for its host. See, the archaeon was anaerobic. Rather than metabolizing oxygen, free oxygen was poisonous to it, which was becoming increasingly problematic as atmospheric oxygen levels spiked. On the other hand, the bacterium was aerobic. Energy likely came from oxidizing organic forms of carbon. Together, by incorporating the bacterium, this archaeon gained its powers. This was an absolute revolution in energy production, for reasons I'll get to. This would have started as a symbiotic relationship between two separate life forms, more specifically endosymbiosis, which is when one party lives inside the other. But over generations, the archaeon and the bacterium exchanged genes, learned to reproduce together, and eventually became a single organism, the first eukaryote cell, with the bacterium shedding genes until its entire function was energy production, and it became what we now know as mitochondria. The importance of this wasn't just to enable survival in an oxygen-poisoned environment. Life was approaching the limit of its ability to adapt to changing environments, because cells were near the limit of complexity. In general, larger cells can incorporate larger genomes and so support more complexity, but larger cells also require more energy, and that energy requirement scales with the volume of the cell. But energy production requires the exchange of electric charge with the environment, and so the amount of energy that can be produced is a function of the surface area of the cell. As cell size increases to enable more complexity, the energy requirement increases with the cube of the radius, but energy production only with the square of the radius. That means there's a maximum size a cell should be able to reach before it could no longer power its own activity. But the eukaryote obliterated that barrier by incorporating mitochondria. Now energy production was limited by mitochondrial surface area. the multiple wrinkly mitochondria in a single eukaryote can have a surface area greatly exceeding that of the parent cell. And with their needs so fully met in this new stable environment, these once bacteria could completely devote their time and genomes to energy production. With enormous new energy reserves, the eukaryote could afford to grow its body and its genome, leading to an unprecedented proliferation of new life forms. Biologist Nick Lane calls this an evolutionary Big Bang due to the sudden explosion in complexity that followed eukaryogenesis. And to double down on the astro analogies, Lane also refers to the events surrounding the formation of the first eukaryote as the black hole at the heart of biology, because there's a hole in our understanding of the evolutionary steps between the three great branches of the tree of life. For example, we're unclear on which of the many unique features of the modern eukaryote came before and which came after the first incidence of endosymbiosis. That also means we don't know how fundamental a shift this really was, and so whether it's really a good candidate for a great filter. But the new study by Enrique Muro and collaborators may shed light on this. It turns out that around the same time as the great oxygenation and subsequent snowball Earth catastrophes, along with the maxed out cell size crisis, there may have been a sort of computational crisis, a bottleneck in evolution's ability to find molecular machinery to solve the mounting challenges of a changing environment. And the solution to this issue coincided with the formation of the first eukaryote, and so may add a critical detail to why this event was so important. Here's a summary of the study. These researchers looked at gene length and protein length for over 6,500 species to study how both of these increase compared to each other, and also how increasing gene and protein length corresponds to when that species emerged on the evolutionary tree of life. The latter is considered to be a proxy for evolutionary advancement and complexity. For simple life forms like prokaryotes, bacteria and archaea, they found that gene and protein length track each other. It seems that over time, genes got longer and so coded longer proteins. The longer the protein, the more possibilities for its mechanical function, enabling more complexity in the cellular machinery. This part isn't surprising. For prokaryotes, almost all genes code for proteins. They're read off codon by codon to construct proteins, amino acid by amino acid. These proteins then fold into various forms to become the molecular machinery and genetic regulators of the cell. But as evolutionary time went on, a phase transition seems to have occurred. Genes continued to grow, but protein lengths capped out at around 500 amino acids and didn't get much longer. So what exactly happened? Why did protein length suddenly become decoupled from gene length? It seems that it was due to what the authors of this study call an algorithmic phase transition. As I mentioned, prior to this decoupling, DNA was almost entirely used for protein coding, and proteins were the machinery and managers of cell construction and operation. That means that the development of complexity was tied to the rate at which evolution could find new and useful proteins. Finding a useful protein means both finding an ordering of amino acids and finding a useful folding of that sequence into molecular machinery. But the number of ways to fold a protein grows exponentially with protein length. By the time evolution had explored the space of possible proteins up to a few hundred amino acids in length, it started to become computationally infeasible to continue to explore the space of large protein folding. So, although it was still possible to find novel uses for current proteins, finding new proteins now took longer than the evolutionary timescale. In other words, by the time new useful proteins emerged, they were no longer relevant. It makes sense that protein length stopped increasing at this point, but this new research shows that gene length continued to grow. So what was all this extra genetic material doing if not coding for proteins? We've known for a long time that most of the DNA of complex life is in the form of these non-coding sequences. They play various roles. There are sequences that code for RNA molecules that play other roles besides protein transcription. There are regulatory elements that promote or suppress the transcription of nearby genes. There are introns, which allow gene sequences to be spliced during transcription in flexible ways. And there's a bunch of stuff that may do nothing or may serve functions that we don't yet understand. In a modern eukaryote, only a small fraction of the genome directly codes for proteins compared to most of the genome for prokaryotes. So, what happened to allow this radical shift? In essence, life found a new way to regulate protein transcription and general gene expression that did not depend on the proteins themselves. If DNA is a sort of computer, then life just found a much more efficient operating system. Among other things, this enabled a massive improvement in life's ability to search the possible space of useful proteins and in the regulation of when and where these proteins are transcribed. And according to this study, this algorithmic phase shift happened around 2 billion years ago, corresponding to the emergence of the eukaryote cell, and at the beginning of the rapid increase in complexity that followed. So let me recap and bring it back to what this has to do with the Fermi paradox. We have a biosphere that's capped out in its ability to evolve. Cells have reached the maximum size for energetic reasons, and DNA has reached the limit of its ability to explore the space of new protein function and regulation, so we're at the energetic and computational limit. And then, at around the same time, both problems are solved with the integration of mitochondria into an archaea, and with the upgrading of the DNA algorithm. Which happened first isn't clear. Perhaps solving the energy problem enabled the larger genomes needed to stumble on the algorithmic solution, or perhaps the latter enabled the increasing complexity that then allowed endosymbiosis to happen. Either way, this massive transition happened at the absolute 11th hour when the atmospheric composition and temperature became unlivable for most organisms. With the appearance of the first eukaryote, the energetic and computational bottlenecks opened out. The resulting adaptation made the current environmental crisis survivable, which was followed by massive diversification. Cells would become enormous and enormously complex relative to their forebears. The first multicellular organisms followed very soon. Another incidence of endosymbiosis led to a eukaryote onboarding a cyanobacteria to give us photosynthesizing plants. Although this second incidence of endosymbiosis could only have happened given the first one, so that second one doesn't really subtract from the uniqueness of eukaryogenesis. This phylogenetic Big Bang may have been inevitable. Maybe endosymbiosis and algorithmic phase transitions are likely if you put enough simple life under enough stress. That may be the case, but the important point is that it may not be the case. The black hole surrounding our understanding of this event means we don't know whether this transition occurred via incremental, relatively improbable steps or a singular gigantic fluke. But if it's the latter, eukaryogenesis becomes an excellent candidate for a great filter. That paints the picture of a universe in which a great many habitable planets form simple life, which goes on to cover the planet, massively modifies the atmosphere, destroys the climate, and then goes extinct. Or somehow adapts in a less interesting way, finds a very boring equilibrium in which complexity remains plateaued at the prokaryote level. Perhaps the galaxy is littered with slime worlds and planet-scale fossil algae beds and not much more. And we might take solace if this turns out to be true. It would mean that the cataclysm or the developmental bottleneck that cut off all of those other potential galactic civilizations may already be behind us. It would mean that our future is out of the hands of statistics. It's our own to screw up or to seize as we cast our eukaryotic legacy to broader spans of spacetime. Thank you to Novium for supporting PBS. Inspired by space, the Novium Hoverpen Interstellar is an otherworldly gift idea for yourself or the amazing people in your life. The Hoverpen Interstellar is available in Space Black, Starlight Silver, Mars Magma, and Neptune Blue, and is refillable. Just as Earth's axis is tilted at 23.5 degrees relative to its orbital plane around the Sun, the Novium Interstellar is at 23.5 degrees, making it easier to pick up. The meteorite-embedded Space Black Edition features a fragment of the Muoniona Luster meteorite, confirmed by a stainless steel certificate. Of course, if you or your special someone prefer a fountain pen, then there's also Novium Future, which can be ordered as a fountain and rollable 2-in-1, or just as a fountain pen. If you're looking for a Father's Day gift or just want one for yourself, there's links in the description below and you'll get 15% off for 48 hours and 10% off after that just by using the code PBS.